I want to be very honest with all of you guys, with my today's audience. I'm quite desperate in just telling the message of how accelerated audio computing is important for audio industry, not just for audio, not just for plugin makers, but for everyone else, everyone that develops something that touches the audio. So today I want to speak about some problems, and I want to bring these problems to your attention. So I will be just going through the slides and reading through them because I was super busy and lazy. So over the past 25 years, our approach to sound has changed little, from recording and editing music to audio playback across environments like virtual spaces such as games and VR, and real-world setups like venues, concert halls, cinemas, homes, and cars. Let's take a look into that and find the key reasons why. So digital audio computing hardware has made very little progress in computing power over the last 25 years. One great example, $5,000 normal retail price without sales, Avid HDX. I'm not sure about the computing capabilities, but it should be like a very few DSP cores running at 450, you know better than me, megahertz frequency, right? Another great example, UAD Apollo, the same thing, right? 6 chips, 6 cores, sorry about my designers, also released more than a decade ago. Let's go and see something else. Dolby Atmos processor, almost $4,000, one chip on board, 64 channel support, right? This version was released in 2019. Another great example of the hardware, this is typically used in vehicles. This is the industry we also want to get in. I'm in GPU audio company. And this is packed with the 450 megahertz DSP cores, right? And it was also released more than a decade ago. So it is quite often where professional hardware didn't receive updates for more than a decade. And what's more disturbing is that it doesn't offer much difference for professional user workflows anymore. You want to do more? Buy more. That's that way simple. It doesn't solve modern professional productivity problems. People spend the same amount of time, and it often doesn't improve the quality of the results. Despite being outdated, it remains expensive, sometimes very expensive, and is certainly not affordable for most professionals. The consumer experience hasn't changed at all. Everyone talks about immersiveness, but do regular people like me, I'm not audiophile, neither I'm audio professional, despite I'm in the industry, I'm high-performance computing scientist, okay? But do regular people actually feel immersed with standard audio setups? Do they notice any difference or understand how an immersive experience is distinct from a regular one beyond the marketing language? In cinema, at concerts, at home, in cars, while playing games. And sometimes, even new audio DSP hardware has a very little progress in adoption. And there's a very beautiful example of it. Sony PlayStation, Tempest DSP. Sony invested a lot of money just to implement on the chip another dedicated chip, which is AMD RDNA 2 chip, to provide this reverberator, convolution-based reverberation effect for their games inherited, right? And the price is included, so whenever you buy PlayStation Pro or whatever, you have this chip implemented. Whereas existing PC-based AMD True Audio Next technology, software technology, could be easily adopted and used instead of creating a dedicated hardware unit that requires a ton of the budget to support, and that just goes outdated at the date it was released, right? AMD has its own technology, and in fact, they already released the games by like almost 12 years ago. The very first game that was released was Thief, and Batman and the other AAA game titles received support of AMD TON engine. Situations like those mentioned earlier won't change until new methods for utilizing advanced audio computing hardware are introduced. Let's speak about the new hardware, by the way. So GPUs, NPUs, TPUs, and DPUs are pretty much everywhere now. So all of these abbreviators, they stand for basically massively parallel systems, SIMD system style kind of, single instruction, multiple data. From the smallest mobile and embedded to the form factors we couldn't imagine 5 years ago. So as you can see, let me have my Jensen Huang's mini-me moment here. This one is Nvidia Jetson Orin NX. So this is a hardware kit. And on the background, on the back of this fan, there's a SODIMM tiny ARM-based CPU plus a GPU that has a 40 teraflops of the computing power. This could be, the price starts with $99 and depends on how much memory you want to put there, etc. And this is a hardware kit with all the peripherals. So what you can do, you can use this embedded GPU to do things that neural DSP, quad cortex, or like mixing consoles of whatever hardware maker offers today, let's say Yamaha, are not capable of doing. You want to run 128 channels with all of the reverbs assigned to each channel, easily done. So this hardware is right here, Nvidia Jetson Orin. Qualcomm Adreno is something that you can find, which I'm a big fan of. Hold on. Samsung moment. Come on, Samsung, you can make it. You can. Yep. This thing, right? So we have Qualcomm chipsets right here with AMD GPUs, right? And these are pretty much capable GPUs. You just need a framework that will allow you to target those GPUs to create your mobile apps or whatever you want, or just to target mobile games with some new experience you want to bring. Silicon that we already support. And what's there? Oh, the Blackwell chip, NVIDIA most powerful chip so far announced. So these devices were created to deliver one thing, accelerated computing. And I was not the guy who started it. There were folks like Jensen Huang and the other guys that started this more than 30 years ago. It began with graphics in the middle 90s, and in the 2000s and 2010s, it saw widespread adoption in scientific computing, HPC, high-performance computing. And after the event called AlexNet, most of you know what it is, it sparked intensive use in machine learning. Designers changed my text. Gosh. So how adoption of GPU technology stack is different for audio? Can we simply use CUDA stack, OpenCL, SYCL, or any other way to just program GPUs and do things DSPs, FPGAs, CPUs cannot do per same computing cost, right? So can we just go natively and just program it low latency and this will work consistently? Native implementations can efficiently transfer data and execute a kernel quickly, with numerous studies already conducted on this topic. So you can have a very quick QR code scanning if you really need to know what is the bandwidth to latency curvature for PCI Express 3.0, 4.0, and so on. I'll give you just like 15 seconds more for those who are interested. There are so many studies. You can just download CUDA SDK, you can run asynchronous streaming example or Graph API example, and you can quickly learn that, yes, I can code GPU really quick, but there are so many problems in that I'll talk about. You can also, which I was saying, download CUDA or any other native framework SDK and run some tests quickly and learn the following. You can run a dummy kernel within a matter of just 1-3 nanosecond. Depending on the PCI Express generation or any other bus generation, you can pack a decent amount of data, megabits of data, within 10 to 30 microseconds data transfer window. So that both comes for round trip and even running some empty kernel. You can even run several graphs of processings within 1 to 5 millisecond latency window. Not bad, isn't it? So yet, this won't allow you to create applications because of these fundamental challenges. Even one kernel For those that are not familiar with GPU programming terms, kernel is just basically a program that you execute on the device. Even one kernel execution latency is inconsistent. You could expect a significant percentile hit with latency drops to 5 to 20 milliseconds. And there is no way to manage it explicitly using existing frameworks functionality. It is easy to break overlapping of streams, meaning overlapping, you can run 16 PCI Express streams, you can assign 16 tasks to run in parallel, but if you break the overlapping, the hardware scheduler of the GPU device will put one after another, and it will break your latency, right? Which leads to unexpected dramatic bandwidth and latency drops. Add to this, over 95% of the audio DSP algorithms are inherently sequential by design, requiring custom parallel implementation. My favorite type of the algorithm is IR type of the filter. By classic design, it's inherently sequential. You cannot run this efficiently on systems such as GPU, right? So you need to find an alternative mathematical approach how to implement this category of the algorithms, right? And even some well-parallelized algorithms such as fast Fourier transform, Kulitukki algorithm, the CUDA implementation for this algorithm as a library spans 85 pages and builds on the scientific research, including an advanced take on the trivial Kulitukki algorithm, right? So it's not that way easy, right? Classic GPU frameworks don't support barrier synchronization for fewer than 32 threads. That means practically when you want to launch, let's say, state space filter that requires only 4 threads or 8 threads, and you will do that with NVIDIA CUDA, you will end up in a situation when you'll have, let's say, for 8 threads, you'll have 24 threads underutilized, which leads to lower occupancy, which means whenever you will run more of those filter second-order sections in your, equalizer, you will end up in a situation just acquiring all of the resources of GPU, but in fact, you will be doing a very little of the useful work. And this is just how CUDA and the other frameworks work, right? As a result, single application often consumes significant GPU resources, which frequently remain underutilized. Real-world applications consist of hundreds of DSP components running in a mixed parallel sequential manner. None of the graph APIs can handle this efficiently without sophisticated device-side optimization and dependency-aware software scheduling, which is, by the way, what we are doing at GPU Audio. And finally, add to this tip of the iceberg some standard engineering problems, such as supporting your application in cross-platform will basically mean implementing a Cartesian product of CPU architecture multiplies GPU architecture, multiplies operating system, multiplies programming model software architecture. So in fact, those who attended yesterday's workshop where we made Neural Amp Modeler open source project running on the GPU for local inference, we mentioned that we support more than 300 configuration implementations for the GPU architectures. The documented behavior, observable behavior, real behavior of the GPU code is still normal, yet undesired situation, even for best-in-class frameworks and runtime environments. So the example that I gave to you guys, if you download NVIDIA CUDA, run a synchronous example, you open NVIDIA Inside Debugger, and you see the overlapping, it just breaks somewhere just because of that, thanks to NVIDIA. And you cannot fix that anyhow. And it works just an example without touching the code. And you see this behavior pretty much everywhere. And believe me, the other frameworks besides CUDA, they are even worse than that. So no wonder that there are almost none of the real commercial applications product exists that utilize power of GPUs. And there are none of them exist doing it truly real time, at scale, utilizing a fraction of the GPU resource and without causing any interference with existing GPU workloads deployed on regular end-user computer systems. We recognize these issues and many others beneath the surface and developed the GPU Audio platform. It provides a CUDA-style C++ interface for programming GPUs along with DSP and neural library building blocks that we presented for the first time on yesterday's workshop. Those who registered ADC attendees, you can just visit Discord at ADC. You can use login and password and visit our website and Jupyter Notebook, and you can just start practicing right away. So we provide the same neural building blocks for your convenience, and we enable the creation of applications, services, and products for nearly any hardware platform and operating system. Let's have a very quick overview on our platform this year again. So GPU audio SDK workflow, it consists of 4 main things. One thing is GPU audio component, which is audio processing engine. It's a low latency software scheduler, really low level one. We implemented using assembly languages for every single GPU architecture. For Nvidia, we use PDX ISA, for AMD, RDNA ISA, CDNA ISA. For M-Silicon, the only way is to go with is metal. If you really want to be consistent in the implementation. We also implement routines and provide APIs. This is all proprietary code provided as a library. Proprietary because we are venture-backed startup, so we need to return money. This is the way it works. So we offer, for this component, 3 things. One most important for you guys, we offer DSP component library there. That contains various already implemented filters, partition convolution, FFTs, neural network building blocks, and so on. So we basically covered all the math implementation on systems such as GPU for you. So you can just reuse and call FFT in the normal way on the C++ side. It is independent of GPU audio, so you can bring your own implementation if you want, any DSP implementation if you are proficient enough. This can be used when writing your own audio effects to do whatever you want to do. We also offer processor API, interfaces for creating audio processors. So this is open header library. This provides necessary tools for creating your own audio effects, and this utilizes our scheduling engine underneath clearly. An engine API, so this is again open header library. This provides interfaces for using audio processor. This provides you tools how to load those processors, how to dispatch them over the time, how to change something for your processing graphs, and so on and so forth. So this is how this basically works between the device and the host side. So basically on the CPU side, you have unified interfaces. You do the initialization, you do compute graph setup, you do port management, you do memory management, you do parameter passing. On the device side, you do all the processor part, which is CUDA, literally CUDA-style programming. You define your context, you define your shared memory usage, you synchronize threads, you do the warp communication or working group communication, you do cache memory operations, and you do your thread management. There are a few entities you need to support to make your functionality work. So GPU audio, this is what we provide to you. Graph launcher, this we also provide to you. The processing graph itself, this is something that you set up. The processing graph holds multiple processors and their connections or ports. The processing graph determines an ideal way of scheduling the graph of their respective hardware, optimizing for number of GPU launches, temporary memory requirements, and latency, right? So you can expect latency going as fast, latency be as low as 30 to 50 microseconds round trip plus execution of empty kernel at scale. That means you can have this consistent latency when you work with multiple channels, let's say tens or even hundreds of channels, wherever GPU is inside this laptop or this mini Jetson Huang thing. And processor, core processing functionality of a processor split into tasks, blocks, and threads running on the GPU. Parameter passing control, memory management, and transfer as needed. And hence, for the GPU audio engine, about processing characteristics like sample rate and so on. Yes, so this is half true. And this is absolute true for 2025. So as of this very moment, the previous day workshop, we already had support for Nvidia, AMD, and M-Silicon. And this all works for Windows, Mac OS X, and Linux, mostly for Ubuntu. I'm not sure about the other Linux versions. But we already know that we support Intel and Qualcomm. Intel is quite a boring thing. I don't want to bring the support there because GPUs are not on the consumer side market yet. How many of you have Intel GPUs that you use? One. I see one. Lucky for you, we will bring support next year. So Qualcomm is, again, right here. It's everywhere. And it's also embedded. It's embedded in the vehicles pretty much everywhere, right? The pity thing is that Qualcomm GPUs are not as powerful as desktop-grade GPUs, but they're everywhere. And bringing Qualcomm and mobile and embedded requires some different techniques to implement. Speaking about Cartesian product that I mentioned earlier. Modern desktop-grade chips include RTX 4080, $1,300. These are all Amazon-listed prices, okay? Radeon 7900 XTX, $750. Gosh, they're so cheap. And M4 Max, unfortunately, $3,200. That price included into the MacBook. So there's also that thing, right? So we have 1,000 cores Nvidia Ampere for Nvidia Jetson or NX. Oh, it's even more. It's for Nano 40 teraflops, and for Orin NX it should be 100 tops, I guess so. And price starts with the $99. But you can Google all of those characteristics. I just don't care about them. And what's more importantly, this person and this thing, which is a Blackwell chip, and Blackwell chip that is embedded into the not DGX, it's something, it's like a server with InfiniBand, with everything, packs up. I think this thing, something around $500,000. DGX 4 unit, I guess, it starts with $25,000. And B200 is just absolutely different world beast. And next year will be a lot of those implementations, starting with data centers because Meta purchased a lot. So those who follow NVIDIA stocks know why they price so much. We also target this. And for us, it doesn't matter what you deploy, where you deploy, is the same thing, the same way being programmed. The power of GPU chips can be harnessed effectively from virtually any location where they are embedded. But is there such a demand for the compute? So let's try to answer what kind of the use cases could be. This is written here as abstract as possible, okay? So there are so many people ask me, why do we need the power of GPUs? Well, if we don't need the power of GPUs, this is the same answer for why do we need to buy an iPhone when we had Nokia back in the day, right? So you can stick just to Nokia and call your mother any moment, right? You don't need those things. You don't need to upgrade your iPhones. Stick to the iPhone 10. Like, don't buy this. So this is the same thing. There's so many ways I can tell you. I can spend like hours on this thing. So for automotive, and we have the first client there, in automotive, in vehicles, you have, let's say in Range Rovers, you have 39 loudspeakers, right? And what you ideally want, you want to compensate speakers so they don't interfere with each other. You also want to compensate car cabin acoustics. And no wonder Range Rovers have NVIDIA Orin, exactly the same chip, in the 2025 model lineup, as well as Qualcomm, which is a part of infotainment system. So you can pick any of those and you can implement your IR-based compensation inside the cabin, as well as you can run digital limiters, so whenever you will be driving and listening to your favorite, let the bodies hit the floor, and then turn left, you can do like limiting from the bottom and from the top, and actually normalize the volume of whatever audio experience you have. Multi-zoning, so many things. Noise suppressing. Whenever you have a call over hands-free and you talk to your colleague, you want your kids that's sitting on the second row watching cartoons, listen to the cartoons, not to your call. That's so many scenarios can be run by software-defined GPU-powered audio. In the Pro Audio, oh gosh, so we started in the Pro Audio, as you know. There are some of the vendors that we already support, that already have integrated GPU audio technology. I personally dream of making bounce button disappear, okay? The DOS needs to integrate GPUs because GPUs have limitless power. So there is no need to click render again and again, wasting hundreds or millions of human hours on just wasted progress bars. Because you have how many? Like in RTX 4090, you have thousands of cores. So you can use the fraction of those cores to do like ray tracing, not for the video, but for the audio of those projects. So you can render them on the fly. And if you render them on the fly, you don't need to render them anymore. You do something, you click something, you render this part, this stem of the project, there you go, you're all set. So I wish this workflow will be normal, will become a standard for Pro Tools, for other DAWs, but it requires some integration, right? And you can do a lot more of the Pro Audio running machine learning-based algorithms, spatial, multi-channel, so many things. I just don't have a time for it, really. Gaming. I used to play games, now I have 2 daughters. And for gaming, it's really, there are some GPU-based technologies like Tempest for PlayStation. There was AMD True Audio Next, there was Nvidia Physics, and they all became obsolete. There's a reason for that, technical reason for that. So imagine right now, there's one game that Metixar recently introduced, Batman thing, where they do ray tracing sound propagation, but it's all static. It's all pre-rendered. The level is pre-rendered. The level is supposed to be pre-generated and without geometry that can be changed during the play. That's the problem. Imagine if you can have destructible objects everywhere. You can change the geometry like Minecraft, but PUBG. So you can smash the wall, you can make a hole inside the wall, and you can hear what's after this hole. You can, all right. And you can hear hello. You can hear what's after this wall, and don't die, please, anymore. You can hear what's after this wall, and you can use this to precisely point to the enemy. Come on. I can see, hear everything. So for gaming, right? For AI machine learning, I shouldn't be explaining to you how it is important. All of these things starting with training, and now with our platform, real-time inferencing, you can host really large neural network models locally. And for producers, this is extremely important because they don't want to get their models going out of the systems they own, right? They don't want to treat corporations with data, with everything they input for this data. And this is just yet another our commitment to the AI-based future, right here. It looks sexy, almost. So I can actually speak like that. Just save a time for. Oh, okay. So I need to go back, right? It's actually it shows something. Yeah, just mirror. Okay. Perfect. All right. GPUs. Let's go full screen once again. Come on, Mac. Okay. So there are so many use cases, okay? The first one that we already presented, we have Vienna Symphonic Library, the first partner. You can download MIR Pro 3D, which is convolution-based reverb. It has a GPU power button. When you hit this button, convolutions, most computational-heavy operations being offloaded from the CPU to the GPU. We can reduce CPU usage from 100% down to the 10%. We already demoed this at the ADC previous year and at the NAMM show previous year. We also have another vendor, Mantra, and we presented for the very first time 64 channels combined in fifth order ambisonics rendered real time with 3D GUI all connected in the form of the VST3 plugin. Right there in our booth, you can just hear it. You can watch this thing happening for the very first time. That means next generation application is out there. And audio modeling, we will be supporting Swarm engine, I hope, really soon. We already passed the processor implementation to our partners. All they need is just to release the GPU-powered product to their customers. In gaming, we have no one, empty hands. We need someone who can help us implement dynamic sound propagation. And whenever we want to manipulate with geometry, change the geometry, and also manipulate with destructible objects, we can make sound not just immersive, but actually utilitarian. Game players can use the sound to play better. Automotive audio, so you may wonder, like, what the hell is about automotive? But every single audio company wants to be in the car-making market. This is something that I learned this year. They have 2 ways to utilize GPUs. GPUs either a part of infotainment system, so this dashboard, this console, middle console, that powers up by GPU, or GPU is a part of other system that makes your pilot driver assistance system work. So you can tackle like 5% of the GPU power to run all of these scenarios combined. Just for you to know, sometimes infotainment systems are made of 40 DSP chips, and it can be as expensive as $500. You can get rid of it if you use just a fraction of the power of the GPU, right? So it's both cost savings and some new functionality you can bring into the vehicle. Gen AI, I personally invested in one tiny company, in one startup that provides some voice solutions for the call centers. They use GPU and CPU implementations, and they also provide some algorithms to speech synthesis. But surely Gen AI is not about that today. It's about Suno and this kind of startups, but I don't want to give them credits here because, yeah, you know why. Okay, it all looks like we can do more, or we can just run advanced algorithms, but how come it can change consumer experiences, right? How it make difference for regular people, right? Like my grandmother, right? So the answer is, it already does. And I stole this picture from Holoplot. Holoplot modules use FPGAs to control loudspeaker channels that perform real-time advanced beam steering and wavefront synthesis. So any of you guys, I wish you experience Las Vegas Sphere thing. You can hear the Doppler effect. Like you can watch 200 meters tall elephant making a stomp with his foot, and you can feel the sound propagates towards you. You can feel at low frequencies with your own bare skin, bouncing back from the venue and going again forward. It's just crazy. So Holoplot system, it has 96 tweeters inside one module. One module also have an FPGA. And the cost of this model starts from $40,000. And Las Vegas Sphere, this gigantic thing, it has more than 170,000 channels, right? And they mix those channels using a server rack. So it's a lot of the continuous constant processing power they require. So you can downsize this thing if you use computing power. And I believe to make loudspeakers multi-modular is not as expensive as actually running something on that thing.
We're gonna have to wrap up, Sam.
Yeah, I'm trying. I'm like doing my best.
No, but we really need to wrap up. So sorry. We let you go 5 overs. You made up the time, but my apologies.
So how much time do I have?
You're quite over already. So
Okay.
Yeah. So sorry.
Yeah. So it can be less expensive. So what we need actually to bring and unlock all of this experience, we need a standard for this. And the name for it is accelerated audio computing. To solve some of the challenges, one of the challenges that we already presented last year, so I'm just gonna skip it. This challenge is about just make GPU audio natively implemented on the VST3 audio unit and AX standard. so we don't waste CPU cycles whenever we call plugins that powers up by GPU or any other external hardware. I'm just skipping that. And yeah, be the first to join the open conversation of accelerated.audio. So we bought the domain. You can scan the QR code. There's clearly no website there. There's just like follow, subscribe for newsletter. So please just scan the QR code and hit the follows us button. And the final next steps, we're going to release our SDK January 2025, hopefully. And the first release of the SDK will be exactly NUM modular workshop that we presented yesterday. So you would be able to run everything on multiple platforms yourself. For those who are interested to experience this today, you can just, again, visit Discord of ADC, use the login password, and log into our Jupyter notebook and try out today. Thank you.
And for our, thank you, Alexander. For the Q&A, I do encourage questions. So please, if you have questions, bring them to Discord.